Hello everybody, and thanks for listening. This is the first time I've ever spoken to such a large gathering with so much technology at my fingertips, and I don't know how to manage the technology at all. Somebody's helping me, I hope. I want to say a big thank you to Jerry Pollock for inviting me here. And yesterday, as I was on my journey to Bulgaria, I was wondering how to get started, and I was feeling quite scared of speaking, because I am not a scientist in the way that all of you, or most of you, seem to be scientists. I have not got a scientific degree, I do not teach science in a university, and I have only passed one scientific exam in my whole life, and that was at the age of 50 plus. And I got a mark of 41%, and the pass mark was 40%. But I'll tell you very quickly how that came about. Some of you probably wouldn't even count it as a scientific examination. It was on human physiology, generalised human physiology, digestion, vision, hearing, and so on, as part of a university training in midwifery. Until recently I was a qualified midwife, and I'm now retired. And the course had chemical equations, ions, H plus, K plus, Cl minus in it, and you can't see an ion, you can't smell it, you can't touch it, you can't hold it in your hands. So something like that, to me, is very difficult to understand. And I saw myself failing this exam and getting thrown off the course. So I worked very hard for a few weeks with an aim of getting 45% in the exam. Knowing, of course, that if you plan for something, there's an error rate, and if I aim for 40, I might get 35 and fail. So I aimed for 45, and I got 41, and I consider that the great academic achievement of my life, because I'm no good at academic science at all, or I wasn't any good anyway when I was at school. But I am a self-taught scientist, and I think I can claim to be a scientist with a little s, in the way that a 3 or a 4-year-old scientist is. You know, if you watch a 3 or 4-year-old child fiddle about, what happens if you do so-and-so? What happens if you add this to that? And they have no prejudices about what they expect to find, those prejudices that Rupert Sheldrake spoke about. You know, they just see what they get, and if they get something, that's it. And that's the way I would work. So let's get down quickly to the actual meat of the matter. Robert Brown and Brownian motion. Is there anybody in this room who's read Robert Brown's original 1828 paper with a great big long title that starts microscopic observations on blah blah blah? Nobody's read it. Yeah, I thought that would be the answer. Well, one person, right. Well, I hadn't read it when I started out. How did I get to that point? I've been a student of the work of Wilhelm Reich since I was about 22. I don't know whether any of you are familiar with his work. And one of the books of his that really hit me back there when I read it was the cancer biopathy. And the one thing I wanted to do after reading that book was to repeat the Brownian experiments, and I had to wait a long, long time until I had enough money to buy a decent microscope. It was 97, and I first read the book in about 1962. And I did the experiments like a beginner, a nervous beginner, cooking their first meal. Here it is, the Brownian experiments of the origin of life in one hand, and my microscope here, and I was following the instructions very carefully, exactly as detailed in the book. And it turned out that when I repeated Reich's basic experiments, that I obtained the results that he claimed I should obtain. Now, the original Brownian experiment was the observation of disintegrating grass underwater. And Reich got to that point from his observations of his psychotherapy patients expanding and contracting as they experienced pleasure or anxiety. And he wrote a very interesting book which I do recommend to you. I think it is in the list here. The Biolet... No, it isn't. Anyway, the Bioelectrical Investigation of Sexuality and Anxiety. And if sexuality and anxiety worries you, you can just replace that with expansion and contraction. And he wondered whether this process of pulsatory expansion and contraction was a basic biological function observable throughout nature. And he planned originally to observe larger marine animals. For some reason that's not documented as far as I've been able to ascertain, he lowered his horizons and limited himself to amoeba. And he found, of course, as any microbiologist knows, if you look at amoeba under the microscope, they reach out, pseudopodia, they expand, and if you put something nasty in the water, they contract. So he asked the silly, this is the 3 or 4 year old speaking, he asked the question, well, where did the amoeba come from? And he was told that they come from spores attached to the grass. As if you just chop up some grass and put it in water, in a few days you'll have some amoeba. And he didn't swallow this explanation. He smelt a rat and he thought he would have a look at what really happens when you put grass underwater. And he examined that carefully. He filmed it under time-lapse filming. This was in the 1930s in Oslo, where he was in exile from the Nazi government of the day. He was on the Nazi government death list and he was on the communist death list, which is quite a distinction. And his books were burnt by the Nazis and eventually they were burnt by the American government in the 1950s. So, as he observed grass disintegrating underwater, he came across a process which, as far as I know, is completely ignored by mainstream science to this day, what he came to call biomass disintegration. And if you watch a blade of grass underwater, you'll see its pristine structure with the cells, the rectangular cells. And after about 24 hours, you'll see dots all over it, especially where the cell walls meet. I'm sorry I haven't got a still of this, but there is a picture of it in my book. And I've got a few copies of my book with me. That looks like this, and it's called Artifices of Fraud. And these dots start to move and detach themselves from the surface of the grass and swim about in the water surrounding the grass. And the surface of the grass itself starts to rock and move a bit like I imagine the earth moves when there's an earthquake. I've never been around an earthquake, touch wood, so I don't know. Doubtless some of you from America and Asia have experienced earthquakes and know what it's like. And bubbles, what he called vesicles, an obvious word, isn't it, formed at the edge of the grass, with some of these containing colonies of these little dots, spinning and pulsating, expanding and contracting, and eventually broke away from the edge of the grass as what I would call a proto-organism. And he made time-lapse photography in the 30s, film of this, and that film still exists and may one day, someday, end up on disc for purchase. I know that they're working on the project at Organon, which is the Museum of Rice Life Work up in the northeast of the United States. Once he'd seen this process in grass, he tried solid materials like ash, ground up soil and sand, and in particular iron filings. And he found that he saw the same vesicles, highly charged, highly motile energy vesicles, emerging from virtually any ground up material, finely ground material. that's disappeared. It's okay, Anthony. Maybe you can start the video now. Now, the grass infusion experiment is a little complicated to film, and there's all sorts of problems with it's open to the air to a limited extent, and of course you get contamination from airborne bacteria. Yes, okay. Just start with the first one. And one of the very simplest experiments described in the cancer biopathy, it's on page 25, I can remember the page reference, was a single iron filing on a microscope slide placed underwater or a 0.1 solution of potassium chloride. Rice chose potassium chloride because he associated potassium ions with the expansion function of the autonomic nervous system in animals, and he thought this would aid the process of expansion. Now this is a single iron filing that a minute before it was placed on the slide had been heated to red heat. So that rules out contamination, and the slide had been sterilised, flamed, the cover slip flamed. And if it's okay, I'll just speak over the video. This explains what I did. And you'll see as the process develops, you will see unmistakable clusters, agglomerations of the biomes, forming pulsatory blobs, to use an everyday word in English. This actually, I'm misinforming, this is a stainless steel filing, but it's, it's still basically it's iron, isn't it? Now you can see, have we got a pointer here? Is there a pointer, a laser pointer, anybody? This is it. That's it. You can see up here, if you look carefully, you'll see 2 and 3 and 4 biomes. And at the final stage of the video, you'll see some of them contracting and expanding, bending. This is just evidence for YouTube viewers to show, to confirm that I'm not making this up, to check that it is there's the steel component, checking that it is in fact steel and not something else. This is a refined finding. You can neglect this, it's not too important. It's important to people who are working in the field, but it's no big deal. What I want to show you is the video at the end stage. Now if you look carefully here, you can see little dots emerging from the wall of the steel filing. And you can see the agglomeration spinning and bending. There's a very good example there. Now remember, this was red hot 10 minutes ago, this filing. There's another good one there, same one there, developing. Now, somebody used a quote earlier. I wrote it down. The dance, water dancing to the tune of matter. Well, I don't think you could get much better than that. There's a picture of matter dancing. This is, as I say, this is extra comment for people active in the field. It's not too relevant to my presentation at the moment. What I want to say is, why have I've condensed a lot of information into a very small postage stamp really at the moment. Why have I picked on Rice's work with the bions as opposed to all sorts of other really interesting parts of his work? And it seems to me that this is a very easily replicated experimental area where you can actually demonstrate that something happens that mainstream science says should not happen. And going back to Rupert's presentation, I couldn't agree more almost with every word he said, but it seems to me that it's really important to pull out, to tease out areas where mainstream science has just got it wrong, you know, where you can actually demonstrate different findings. I have visions of this tiny little gesture, someone getting hold of a brick in a foundation and pulling and rattling and wobbling, and eventually that one tiny little brick of the foundation comes out. You know, all of you here pulling on different bricks, and if we all keep pulling enough, as any builder or architect knows, you don't need to get many bricks out of the foundation before everything starts to collapse on it. Now, how long have I got left? Skål till I wanted to leave some time for questions, so I think maybe I'll stop there for a few questions. But if you've got a little limited question on some tiny personal limited area, please leave it to over lunch. But if you've got a good question that's more general, that might illustrate something for everybody here, then please ask it. I have moved very quickly, jumped over lots of ditches without going into things in detail, and just scratched the surface really. I've not looked at my notes at all. Yes, let's go straight back very quickly to Brown. Now, if you go back to Brown's original paper, you find all these forms that Rice rediscovered, I would say, described by Robert Brown. And in the interpretations, in the descriptions of Brown's work, in the textbooks, in the summaries of his paper, you don't find any mention of these agglomerations, which Brown describes very accurately, and strings of his active molecules. What Rice called bions, Brown called active molecules. Molecule in his day was just a word for any very small microscopic particle. And he describes these pulsating agglomerations of molecules and rotating agglomerations of molecules. What he describes doesn't fit the bill of what you see in the physics textbook of Brownian motion, the description of Brownian motion. And when I first achieved, as it were, first replicated Rice's early experiments, the classical ones, I thought I'd better read Brown's paper, because the objection to Rice's findings was Brownian motion. He showed his cultures to scientists and they said, oh, Brownian motion. And the other explanation, of course, was contamination. So I read Brown's paper. It's not in print, but if anybody wants it, I can give you the text online, transmit it to you. You find these descriptions, which are virtually word-perfect descriptions of the things that Rice describes. And yet, what I call the neutered version of Brown's Brownian motion, in inverted commas, is repeated again and again, just like gossip. If somebody says something nasty about a person, it's gossip. Person A, person B hears it and repeats it, and person C hears it and repeats it, and so on and on and on, again and again. If you collect explanations of Brownian motion in textbooks, it seems that that is what's happening. People I have met physics teachers who tell me that they teach Brownian motion, and Rice describes the same scenario in his book who teach Brownian motion as they are meant to, as per the textbooks, and they have never yet seen it themselves. They are just teaching a hypothetical version that exists in the books. So I do urge you, there must be many, many of you here who've got access to microscopes. Yes, hands up, those who've got access to a microscope. Oh, not as many as I thought. Anyway, a good enough number anyway, maybe 20% of you. These experiments are quite easy. If you're versed in microscopy, this iron filing experiment, it would take you half an hour to do it. It would take a complete beginner, because I have shown complete beginners how to do this experiment in my improvised laboratory at home, which is a spare bedroom with no running water in it. And people have been doing these experiments after an hour's instruction, so it's no big deal. And there's a student of mine, if I can call him that, I've never met him, an online student in Canada, who is repeating these experiments one by one on a microscope which he found in a dustbin, what you Americans would call a trash can, I think. He worked in the hospital as a porter. He saw a microscope that had been thrown away in the trash can. He pulled it out, he took it home, and some months later, maybe years later, I don't know, he heard about me, he found me online, and bought my book, and was inspired to clean up the microscope by one missing objective, and he's already doing good biome research with this microscope. It's got a maximum magnification of 900x. So you've got no excuse, just go home and get on with it, please, some of you. My dream is that some university student in years to come will be listening to a professor, listening to all this stuff about Brownian motion, and he stands up at the back, or she, and says, "Excuse me, Professor, no, you're wrong there. I've done the experiments, and the experiments show that Rice was right, and that Brown was the original discoverer of the biome in 1827. He did the work in 1827, published his report in 1828. I've got several more videos of this, which I won't bother showing now. Obviously, I'm out of time. But if anyone wants to see these videos, and we've got a laptop available, then you know, we can have a look at them outside. Okay, thank you.
Now we have the time for discussion. Question, please.
Is your main point, I just want to make sure that I have it right, your main point is the complexity of the motions, that, right, the rotational motions and such, is that the point that's incompatible with the current explanation for Brownian motion, or does it go beyond that?
Good point. You see, I was skating over things so quickly I forgot to mention that. That's the beginning of it, yes, the rotatory, the spinning, the basic movement of a biome. When you get one biome bracing away from the grass, or bracing away from an iron filing, or rock dust, or whatever you use, the characteristic movement is this ferocious rotation. And the other thing that you see is pairs of biomes beginning to dance about each other in a rhythmic attraction and repulsion. Now that sounds quite convincing, as if it's some basic function, attraction and repulsion, doesn't it? But the funny thing is, at some point, I don't, and I don't think anyone knows why or how this happens, the repulsion is overcome and you get your agglomeration beginning. Now that can't conceivably happen as Brownian motion, can it? As I understand it. And if you watch, you have to watch for a long time, very carefully. Occasionally you will see the two together, and suddenly you will see a third one approaching and shooting in. Now what makes the third particle decide, in inverted commas? This, I think, bumps up against your idea of memory and water and Rupert's transmission of information. What you would call morphic fields and what I would call an orgone energy field of mutual attraction. But you can see it happening. But the thing is, you know how the only people who make see new things in astronomy nowadays and in bird watching, for instance, are amateurs because they're the only people who have time to sit there, watch and watch and watch. A professional scientist doesn't do that anymore. And I was watching, sometimes I just look at a culture, you know, for a couple of hours to see what I see, and once I suddenly saw this third biome whizzing in. Now, if I had to watch, say, for an hour to see that happen once, in 0.1 or 0.2 mils of fluid containing a culture of ground up rock dust, that process is going to be happening zillions and zillions of times throughout nature, isn't it, if you see it once on a slide. And once you get more than 2 or 3 together in a unit, you get this pulsatory bending movement, which would connect to human sexuality and what is called the orgasm reflex, the pulsatory motion, which is, you can see it's not just a sexual reflex, you can see it all throughout biology, you know, in insects, worms. This is the sort of thing that sends a 3-year-old through the roof in ecstasy, you know, watching a worm or a shrimp or something, doing this lovely pulsatory movement. The jellyfish, that's the good example to see. Does that answer your query?
Yes, thank you. Yeah.
Question, thank you. Jenny, microphone.
So we're taught in science that Brownian motion is nothing more than the random walk.
Yes,
Of
yes, I know that expression. Yeah.
Due to, we're told, atomic and molecular bombardment.
Yes, yes, yes.
And yet it seems, from what we've learned about colloids, going back to Picardy, that they're not independent from even geocosmic forces, the phase of the moon, solar flares, that these have influenced the motion and the aggregation of colloids. So we have bits and pieces of a science that shows us that we can't separate the bion or these small particles from the rest of the universe, in fact. That the minute we make a system and we think it's isolated, we find out that it's hitched to everything else in the universe.
Well, that's exactly what Rupert's talking about, isn't it? Yes. I mean, I have, for the purposes of my talk, I have isolated the biome, but I couldn't agree more. You know, and I could talk all day about that. And it probably even the energy field of the experimenter affects the results you get in the biome.
So I think a definitive experiment that could be done today would be to investigate the motion with image analysis software and really look for the randomness or the non-randomness in relation to field effects, to other phenomena, and to set this question straight, whether it's truly random or whether it can be shown to be influenced and beyond random, beyond...
Yes, I agree. Yes. That's all I can say.
Last question, last question, last answer. Professor Wysocki, you.
Well, if you ever wanted to do this then, if I just may ask, if I take my graduate students and I want to have them do that little experiment you just talked about, I'm sorry, would you mind just briefly then say, what do I do when I get back with my microscope with my young graduate students, interns, residents? They're trying to learn what you're just saying about, what should I do? Should I take a drop of water? And then put
Well, could we do it over lunch or something? It's in my book. It's in great detail, but I'd be very happy to talk about it to you. Yes. That's a dream come true. I've imagined Richard's school sixth form biology class repeating these experiments. So if you're going to do it in an American university?
Yes.
Wonderful. Yes, marvelous. Right, talk about it later.
So, thank you once again.